So last class we talked about how the electrons are arranged in energy levels inside of an atom. And we ended up with the Bohr model, which basically says that the electrons exist in little orbits, in little circles, kind of like this, where you've got the nucleus, you've got the first energy level, the second energy level, the third energy level, and so on like that. Well, it turns out that that's not exactly the case. Okay, so how do they? How do they exist? They don't quite circle around. They exist in these areas of space, and they kind of move like bees moving around a hive in very random paths. So, and they don't exactly they don't exactly exist inside an orbit like this, a nice circular orbit. They exist in a three-dimensional region in space, which is called an orbital. Now, there are several different kinds of orbitals, and we're going to start talking about them all as we go through the day. Okay. Orbitals, they come in different shapes and sizes. We don't have to memorize these shapes. Well, yes you do. You're going to have to memorize that shape and that shape for an S and a P orbital. Okay? So an S orbital is basically a sphere around the nucleus. A P orbital, this is one example of a P orbital, it looks like a bow tie or a propeller. And there are three different types of P orbitals. One going up and down, one, here's see if I can draw the axes like we've got them here. That one went up and down on the z-axis. There's another type that goes along the y orbitals, okay, with a y-axis. And there's another type that goes along the x-axis. Okay, so those are all different types of p orbitals, and that gets filled in like that. Okay, so three different types of p orbitals. They all look like bow ties or propellers. Okay. Over here we've got d orbitals. They kind of look like flowers. All right. Except for that one. I don't really know what the deal is with that one. But we're going to figure out today, over the course of the day, how to arrange electrons inside each of these types of orbitals and the rules for putting them in. Okay. So that's going to be called the electron configuration. Let's take a look. The diagrams below represent the orbitals, remember the S and P and D and F orbitals, that are available for the first 10 elements on the periodic table. As you go from bottom to top, the orbitals are getting higher in energy. Makes sense. Bottom of the page, lowest in energy. Okay? Each box represents an orbital. Remember, they're very, very different types of orbitals. Okay? And they're also different energy levels. Okay? We're going to talk about all of that as we go. Certain rules for how you fill in these boxes, we're going to instruct you on those. And we're going to use arrows to represent each electron. Okay. What we're going to do is we're going to start at the very bottom. Okay, we're going to start at the very bottom. Hydrogen, if we look on the periodic table, has one proton, which means a neutral electron, or neutral atom of hydrogen, will have one electron. Remember, electrons are lazy. Electrons are very, very lazy. So if they have a choice, they're going to go in the very lowest energy level possible. So this one arrow, this one electron, is going to end up in what we call the 1s orbital. That is the lowest possible orbit, or orbital, lowest possible energy. Okay? Now, for helium, which has two protons, which means it has two electrons when it's neutral, we can go ahead and write in a 1 electron there, and we're going to put another electron there. We're going to find out why. The arrows should be in opposite directions. Now, come down here. The electron configuration is basically a way of taking this diagram. This is an orbital diagram. This is another orbital diagram. The electron configuration is basically our way of saying, taking this orbital diagram and making it easier to write. The electron configuration for hydrogen is written as 1s, so that's the orbital in which there is an electron, and then 1s1, since there is one electron in that orbital. For helium, the orbital name is 1s, and there are two electrons in it. Okay, so the electron configuration would be 1s2. Now, there's a rule that says no more than 2 arrows can be placed into one orbital. No more than 2 electrons can be placed into one orbital. when two arrows, or when two electrons, they must have opposite spins. That's something called the Pauli exclusion principle. The Pauli exclusion principle. We're going to get into a little bit more what that is. Come down and take a look at the next one. Lithium has 3 protons, so it's got 3 electrons. The first 2 electrons are good. They can go into this 1s orbital. But Pauli says that no more than 2 arrows, no more than 2 electrons can be placed in one orbital. Which means then the third electron is actually going to have to go up into this 2s orbital. And that's a problem. The electron configuration for lithium start at the bottom. 1s, there are 2 electrons. 2s, there are 1 electrons. I would read that as 1s2, 2s1. Beryllium, 4 protons, which means it has 4 electrons. 1s gets 2, and the next 2 electrons can go into the 2s. So beryllium would be 1s2, 2s2. Look at your periodic table. Well, this is not really the case because we don't have electron configurations on our periodic table anymore. We're going to flip to the next page. There is another rule. It says when you have more than 1 orbital on the same level, each orbital must have 1 electron in it before any orbital can get a second electron. Think about it like seats on a bus. Okay? If there are 3 seats on a bus, usually those 3 seats are each going to have 1 person in them before any of those seats has two people in them. You're not going to sit down next to somebody if there's an open seat that you can take all by yourself. So let's see how that's going to work with boron and carbon and such. So we're going to use Hund's rule. That's the seats on a bus rule. Okay? Elements 5 to 10. Boron, 5 protons, means we have 5 electrons. Boron, the 5 electrons, the 1, 2, 3, 4, okay, since we can still fit 2 electrons into that 2s, the 5th electron has to go to the 2p. Carbon has 6 electrons. 1, 2, 3, 4, 5. Then the 6th electron, it's got a choice. It can sit down in one of the empty seats, or it can sit down next to this other electron. It's going to choose the empty seat every time. Nitrogen, 7 electrons. 1, 2, 3, 4, 5, 6, 7. Notice how each one of them has their own seat. Each one of them, the electrons, has their own orbital. We get to oxygen with 8 electrons. Things change up a little bit. 1, 2, 3, 4. Now 5, 6, 7. They're each going to take their own orbital. The 8th electron is unfortunate. It needs to come back and it needs to pair up. For fluorine with 9 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9. And neon with 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice how we actually fill up all 3, or we add 1 electron to all 3 of them before we go back and add a second to any of them. That's going to be, we're going to be following Hund's rule each time we do that. So let's go ahead and write boron. I see 1s2, 2s2, 2p1. For carbon, 1s2, 2s2, 2p, and we're going to take the total number of electrons in the entire 2p sublevel. Okay, so this is a sublevel, the 2s sublevel. All of these are the 2p sublevel. Okay? There are 2 electrons at the 2p sublevel. Nitrogen, 1s2, 2s2, 2p, 1, 2, 3. Oxygen, 1s2, 2s2, 2p, 1, 2, 3, 4. Fluorine, 1s2, 2s2, 2p, 5. 1s2, 2s2, 2p, 6. You'll notice that the electrons keep adding up by 1. And you'll notice also that the total number of electrons here, 1s2 plus 2s2 plus 2p5, 225, together equals 9 electrons, which is exactly what we have here in fluorine. Next page. Scoot down here a little bit. Fill in the remaining symbols, arrows for elements 11 through 18. Write the electron configuration in the blank next to each symbol. These already have the first 10 electrons filled in, 2, 4, 6, 8, 10. So what we need to do is add the rest of them. Sodium has 11 electrons, 2, 4, 6, 8, 10. The 11th would go here. Its electron configuration, 1s2, 2s2, 2p6, 3s1. For magnesium, 2, 4, 6, 8, 10. It's got 12 electrons, so the 12th are going to go there. 1s2, 2s2, 2p6, 3s2. For aluminum, it's got 13 electrons, so we can go 12, 13. 1s2, 2s2, 2p6, 3s2, 3p1. Silicon, 14 electrons, 2, 4, 6, 8, 10, 11, 12, 13, 14. Remember, they got to take different orbitals before they can pair up. 1s2, 2s2, 2p6, 3s2, 3p2. Phosphorus with 15, 2, 4, 6, 8, 10, 11, 12, 13, 14, 15. 1s2, 2s2, 2p6, 3s2, 3p3. The other thing I'd like you to notice, take a look at silicon and compare it to carbon. Silicon's electron configuration ends 3s2, 3p2. Carbon's electron configuration ends 2s2, 2p2. They're in the same column on the periodic table, the same family, and they have the similar ending to their electron configuration. Nitrogen ends in 2s2, 2p3. Phosphorus ends in 3s2, 3p3. Very interesting. We're going to come back to that. Sulfur, 16 electrons, 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16, 1s2, 2s2, 2p6, 3s2, 3p4. Chlorine, 17 electrons. Here's 11, 12, 13, 14, 15, 16, 17, and that's not an electron, my mistake. 1s2, 2s2, 2p6, 3s2, 3p5. Argon, 18 electrons. Here's 11, 12, 13, 14, 15, 16, 17, 18. 1s2, 2s2, 2p6, 3s2, 3p6. Let's head on to the next page. The orbital diagram at right represents all of the orbitals from 1s up to 4p. If each of these orbitals at the diagram at right is filled with 2 electrons, how many total electrons would be present in the atom? Well, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is boring. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. 36 electrons. Look on the periodic table, assuming it's neutral, that would be krypton. Now, the other thing I'd like you guys to notice is as we fill all of these up, let's just assume all of these are filled. We're completely filled with the 4p. Argon, completely filled with the 3p. Neon, completely filled with the 2p. That's going to be very, very important. And it turns out that anything that has a full S and P sublevel, full S and P sublevels at that energy level, is going to be very important. Notice how many electrons there are between the S and the P. 2 plus 6, that's 8 electrons. Full S and P orbitals are going to be something called a full octet, okay, for 8 electrons, and that idea is going to be very, very important as we go forward for the rest of the unit. Let's take a look here. For each of the following electron configurations, give the symbol. Well, that's easy. S2, 2, and 4. That's a total of 8 electrons. which is oxygen. Okay. The other way we could do this is look at it. Well, we'll get into that later. Take a look here. 2 plus 2 is 4, plus 6 is 10, 3s1 is 11. That's sodium. 2, 4, 10, 12, 15. Number 15 is phosphorus. Okay. 2, 4, 10, 12, 18 is argon. Excuse me. We see this written a little bit strangely. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. We haven't really talked about the 3d level yet, but it is a little bit strange. And we see here on this orbital diagram, it goes from 4s to 3d to 4p. This is one of the quirks of electron configurations. 4s fills before 3d, which fills before 4p. We're going to get into why that is, but we'll get to that later. Here, total electrons. We got 2, 4, 10, 12, 18, 20 is calcium. And this one, up to here, we know it's got 10, 2, that's another 18, 20, 23 is vanadium. Here's up to 10, here's up to 18, plus another 2 is 20, 27 is cobalt. Okay? Down here, up to this way is 18, 28, 30, 4s2. 4s2, 3d10 is 30. That is zinc. Up to 4s2, 3d10 is 30. 31 is gallium. Here's up to 10 at the 2p. 18, 28, 30, 32 would be germanium. Okay? And here we have 10 up to 18, 28, 30, 35 is not chlorine, bromine. Okay? Now, this is all getting a little bit tedious. Okay? It's all getting a little bit tedious. So we do have a way to abbreviate all of these electron configurations. Look at magnesium. I'll just give this to you. We look back in the rest of our text, the rest of our notes. It is 1s2, 2s2, 2p6, 3s2. Silicon, 1s2, 2s2, 2p6, 3s2, 3p2. Potassium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Titanium, we've got it somewhere around here, but we look at this, 1s2, 2s2, 2p6, 3s2, 3p6. Then we go to 4s2, that's only 20 electrons. Titanium fills up the 4s and then goes into the 3d. Still got 2 more to go, so 3d2. Iron has 26 electrons, so 1s2, 2s2, that's 4, 2p6, that's 10, 3s2, 3p6, that's 18, 4s2, that's 20. Okay, now we need to put in another 6 electrons into the 3d, so 3d6. Arsenic has gone all the way past the 3d, okay, and it's now filling up the 4p. Arsenic has 33 electrons, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, that gets us up to 30 electrons. It's then got room for 4p3. Selenium is right next to it with 34, so 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4. Now, that gets really boring, really tedious. My hand is starting to hurt. So what we can do is use what's called the noble gas abbreviation. What we're going to do is take a look at magnesium and find the noble gas that comes right before it. Magnesium is number 12. The noble gas that comes right before it, in this case, is neon. Now, neon, if we look back at our notes, neon has an electron configuration of 1s2, 2s2, 2p6 with 10 electrons. Well, check it out. 1s2, 2s2, 2p6, 1s2, 2s2, 2p6. I can replace that part with neon. So I just put that in. I say that, hey, look, magnesium looks like neon, except it's got an extra 3s2 tacked on top of it. Silicon looks like neon, except it's got an extra 3s2, 3p2 tacked onto it. For potassium, its nearest relative on the noble gases is argon. Argon looks like 1s2, 2s2, 2p6. Okay, argon has added on 3s2, 3p6. So up to here, that looks like argon. This is the argon plus a 4s1. This one looks like argon up to the 3p6 plus a 4s2 and a 3d2. Iron looks like argon, keeping up all the way to the 3p6, is like argon, and then it tacks on a 4s2 and a 3d6. Arsenic looks like argon, except it tacks on a 4s2, a 3d10, and a 4p3. Selenium looks like argon, except it's got a 4s2, a 3d10, and a 4p4. The key is to find the noble gas that comes immediately before this one. So sometimes you have to backtrack a good long ways. Selenium backtracks all the way to argon till it gets to be the noble gas. Okay, and the noble gas is always the one in the far right column, column 18 or 8A as we see it. Okay, we're going to get a lot more practice with using the noble gas abbreviation and with writing complete electron configurations as we go.